in getting into outer space. So it's sort of a competition at the time. And you all know it, the first satellite that was sent into space was Sputnik, accomplished by the Russians. So this really was just a goal to get there. There was no science involved. They just wanted to send a satellite to say that they could do it. So the US countered this by sending their own probe, the Explorer 1, into space. So this is whole feedback of like, who's going to get there first? Russians beat the US, and then the US countered and sent out this probe. It had a few science instruments on it, but not too many. It was really just, again, to get there and to prove you could. Moving forward, what's the next logical step? You send a person into space. So the Russians, again, beat the United States, which were, again, were the two really forefront countries involved in this mission, by sending Vostok 1 with Yuri Gagarin into orbit around Earth. So he did one full orbit. And again, this was not good enough for the US, so they kept going and sent their own man into space. So that's Alan Shepard. He didn't quite make it around the Earth, but he got into orbit and came back down. So these were two successful missions, both by the Russians and the US. But neither country was determined to give up. They, again, were going to think, what's the next logical step? So the moon's pretty close, right? So let's go there. And finally, at this point, the United States beat the Russians and sent people to the moon. They also had Apollo 8, which did a lunar orbit and came back. But finally, someone got people to the moon. And you have all these iconic pictures, and it was a big thing in the 60s, 50s and 60s to even send someone here. And this was a really big step for us, for astrobiology and just space engineering in general, because this really was a major feat, just sending anything into space, let alone people. So this really sparked the age of astrobiology and the age of space engineering, and particularly NASA started sending a lot of equipment into space. And they started off one of their main science equipment with the Pioneer series. And in particular for here, Pioneer 10 and 11 were meant to go to the outer solar system. And you know, it was hard enough just to get things to the moon, equipment to the moon. So they had this ambitious goal to get it to the outer ends of the solar system. And incredibly, they did. And it was a really successful mission. So Pioneer 10 and 11 actually went out into Saturn and Jupiter and mapped and imaged these planets, which was completely incredible for the time. So you have these really unique pictures of things that you previously couldn't see from Earth. And this really just kind of took off for a few years. And then they moved on to skip ahead an extra year. They moved on to the Voyager. So that was essentially another a continuation of the Pioneer series with more developed cameras and more instrumentation. So you can see that there's a little bit more complexity to their module that they sent out there. So this is sort of this next logical step in space engineering. You get somewhere, you show that you can do it, and then you start sending more advanced equipment so you can further characterize it, so you send more and more advanced equipment. This makes a lot of sense. So you're getting even better pictures, and you're starting to get some more finite information on the magnetospheres and the radiation environments and what type of minerals you can expect on the surfaces. You're getting better measurements. So this helps your future equipment that you plan to send. And I think everyone knows this one, the Viking experiments that were sent to Mars. Like first NASA sent some stuff to the outer solar system, so they didn't have to worry about landing anywhere. They just sent it out there. Then they finally wanted to land on one of these planets, and that in itself is a whole nother ballgame. And believe it or not, after a few unsuccessful attempts by, again, the Russians and the US, they finally got some to land, so the Viking landers got on Mars. And there was one big handicap here, or one big undersight, where they decided to put a chemistry experiment on it, and without characterizing the mineral content of the surface. So the experiments were a little up in the air as far as the results go. So this really hurt the science instrumentation portion of what they were sending into space, and there was sort of a lull for a long time period, almost 15 years, for where they just weren't really sending anything into space, until we get this amazing piece of equipment, the Hubble telescope, in 1990, and you start getting all these incredible images of the solar system, and it really revitalizes everyone's interest in outer space and space technology. And for its time, in 1990, this was like one of the most incredible developments in space science. So it really just sparked that space science expedition and the whole series of what we were going to even think about sending into space. So the world started sending these telescopes, called the Great Observers into space, and another where I'll come to that one in a second. But first, they send out the Cassini mission. And again, this is sort of iconic in at least our setting for astrobiology, where you have these really even more advanced tools for detecting the sort of environments we'll expect around these planets, and incredibly advanced. So they had another 15 years to get even more advanced cameras. So they're getting better images of the moons around these planets. And I think everyone knows at this point they found the Enceladus plumes. So this again really put a big step forward in the astrobiology community, and specifically because everyone's like, oh, what's on these plumes? Like this is an icy world. There's water here, so there might be life in these plumes coming off of this planet. So the Cassini, as famous as it is, it really just sort of defines the direction, at least for now, that a lot of the science is heading for outer planetary research. So again, this was another one that's sort of lesser known as the Spitzer telescope. It's one part of the great observers. The Chandra is another one. But combining all the telescopes out in space, you can get these really awesome composite images and data from the different cosmos that we can see from Earth or from surrounding Earth. So you can start to really map the entire galaxy and our known universe, which before was really like just a challenge that was so out there that no one could even fathom. So it's like mind-boggling to think about it. But also during that time, there were a lot of really heavy focus on Mars. And it's made me happy that they finally started to send more experiments to Mars even after the Viking landers. And the first thing they did was to send a rover, because they hadn't done that before. They'd only sent landers. So they were first concerned about landing. So now they're concerned about actually moving around on the planet so you can get more data and figure out how to map the area and figure out all the mineralogy. So they sent the Pathfinder and the Sojourner rover, and they were able to land on Mars successfully, which was an amazing feat of its own. They had like the weird bubble system, but it worked. So whatever, it works, it's good. So they moved on from that, and they went to the Spirit and Opportunity, and I think a lot of people have seen this one. It's a picture of Earth. It's a pale blue dot picture of Earth from Mars. And it sort of, it defined where science was at that time. Like we were able to get there. We had these really faint images of all these planets and the surfaces of these planets. And we got to the point where we can see our own planet with these high resolution cameras, and we're getting mineralogy composition of the land, so we can actually start sending more relevant wet chemistry techniques, which we didn't think of in the past. And they did. So they sent the Phoenix lander, which I think everyone knows, saw the water or the water from its collection sample go over time. So you could see that there's liquid water, at least some evaporation over time. And they have another interesting landing technique. They even photographed it as it was going down. And it was, again, a big feat at the time. Bringing us all the way to the Curiosity rover, which had a more advanced wet chemistry lab. So again, there's this whole logical step of progression where you go to where you want to go, just to prove you can do it. And then you start sending more and more advanced technology, so you further characterize the area that you want, the area of interest, and then you send in your really fine-tuned equipment. And some of the future directions, so this is really defining the future directions of space technology for this specific, or for our specific context in astrobiology. So we have the James Webb Space Telescope. That's essentially going to be the Gen 2 of the Hubble, and we're really going to be able to zoom in further on our universe and our solar system as well, to pick out more fine-tuned characteristics. And we also have Europa Clipper, so this is highly relevant to the astrobiology community to look at the Europa environment, so we can send more equipment to actually land on the planet or land on the moon. And the Mars 2020 rover will be sending it back to Mars and gathering samples for potential future collection. So bringing this back to the talks that are coming up, it's really important to go through all the general path of how you send things out into space, because for this talk, for talk number one, they're using X-ray imaging techniques to study microfossils, and we've seen some pictures on Mars where there were microfossils, but it was really, or they were pretending, or they were thought to be microfossils, but we weren't really sure. So we need to develop our own techniques to do that on Earth so we can really hone down on it. So one way to do that is with this 3D topography, and it takes X-ray images and creates a 3D model. You can also do that with micro CT, which they'll be going over after, and same thing with confocal laser scanning microscopy. That's just taking pictures in 3D images. Talk number two, we'll be going over this region-based convolutional neural networks. which is different than just a prediction of what are using an image and picking out spots on the image and telling you what they are. It's actually figuring that out and interpreting that source image to give you what it thinks is actually there. And lastly, looking forward, is this SETI talk. They're using the Green Bank Observatory to look for signs of extraterrestrial life, which in and of itself is a really difficult challenge because it's hard to penetrate through the background noise of the universe. So really looking forward to these talks, and thank you.